In this section, we will explore the two newcomers to Hadoop. These are the Apache Spark and Apache Flink. If you look in the history of Hadoop improvements, we can see that in the beginning we started with plain MapReduce. MapReduce is a rather brute force algorithm, and it is not necessarily the most optimal way to run things. One of the common disadvantages of MapReduce algorithm in its traditional implementation is that it is very I/O heavy. So it would be writing the data on the disk, and then this data will be read again by the subsequent tasks. Apache Tez introduces an optimization mechanism where we don't need to have that many inputs and outputs, but the data can be directly streamed to the next stages in the processing. Tez introduced significant advantages to the processing time, and it made Hadoop moving slowly from the batch into the near real-time execution. The ideas behind MapReduce are relatively old, and a couple of years after they have been introduced, scientists have been working on a couple of alternative mechanisms that are not necessarily using MapReduce. Also, MapReduce did not use a vast amount of knowledge that you accumulated in the area of relational database design, particularly distributed relational databases. So we have two systems that are building on a more optimized, more streamlined foundation. One of them is Apache Spark, which is trying to move more data processing into memory, and the other one is Apache Flink. Currently, Spark and Flink have a number of commonalities, and we are going to treat them both as the new generation of Hadoop systems. Let's see first the key element of Apache Spark. So the important features there is that Spark is trying to use in-memory data structures. And the data structure that is used for that purpose is something that is called a resilient distributed dataset. And why are they resilient? Because if the failure occurs, the dataset can rebuild itself. So basically you have some trace how this dataset in memory is constructed, and you can rebuild it based on your actual data source. Spark is coming with a rich set of operators. Many of these operators are inherited from the design of Scala collection libraries, and the programs that you are writing in Spark will remind you very much to programs that you would write in Scala as if you are dealing with in-memory data collections. Spark is a rather efficient system, so we have seen really good numbers, 10 to 100 times in memory faster than Hadoop MapReduce. Also, the Scala API is very productive, so we have significantly fewer lines of code, 2 to 5 times less code than if you are using rich APIs in Java, for example. The key components of Spark are the following. At the bottom, we have the Spark core engine, and then we have a number of systems on top of that. So we have a Spark SQL that is adding conventional SQL capabilities to Spark. This is going to broaden the appeal of Spark. There is the streaming API, which is combining the batch and streaming processing. So the code that we are writing for both batch and streaming is very, very similar. Then there are machine learning libraries. There are libraries for dealing with graphs. And there is also Spark R that provides the R programming language interface to the Spark. At the time of creating this course, some of these different components were at a different level of maturity. Some of them are industrial strengths, while some of them were in early development. Internally, one of the interesting elements in Spark is the data sharing, which can be happening so that we begin with our data in HDFS. We are executing some code, we are providing some processing in iterations, and we have some result, which is held in the memory of the machines in the cluster. Then we will be processing this data in the second iteration. And then we have the results of that stage in processing again held in memory. And this data in memory can be used to answer various queries. So as you can see, it's a very efficient mechanism which is reducing the I/O and are trying to answer various queries from the data in memory. Apache Flink is the new system in Apache Hadoop ecosystem. And one of the interesting features of Apache Flink is that the programs are compiled into plans. And these plans are then optimized and then eventually executed. So if you're coming from a relational database background, you will say, well, this is nothing new. We have been seeing that in relational databases. There are access path builders, and then there are query optimizers. And now we are gaining the benefits of this type of execution in our Hadoop and big data systems. Flink is a result of a European research project, and it has a couple of goals. First, very high performance, then unification of batch and streaming into a hybrid runtime, and finally, simplicity for the developer. Spark and Flink have many common points when it comes to programming, and ideally you would be using Scala, very expressive language. Few lines of code will accomplish a lot in this setting. Internal data structure of Flink is called the dataset, and it is similar to RDD that we have in Spark. It can be produced or recovered in a number of transparent ways, like using in-memory collections, like an RDD. Sometimes it does not need to be materialized at all, and sometimes it is updated in an iteration. So, the optimizations that we have in Flink is that the optimizer selects an execution plan, similarly to what we have in a relational database, and then the system is going to optimize, and it can use the size of the input files for that. When we are running Flink, we can run it as a standalone installation over our cluster, or we can run it on top of Hadoop. That is convenient because now you can use Flink on top of HDFS. And both Spark and Flink are providing integration with many of the existing Hadoop technologies. To summarize the features and advantages of these systems, they are providing us with ability to run iterative algorithms and do that in a very efficient way. Both systems are dealing with very good caching, and they reduce the overhead in comparison with conventional Hadoop. Both systems are unifying batch and stream computing, and both of them favor Scala as a natural expressive language for big data processing. And there is also support for other languages. Particularly SQL is of interest there, as it will be able to address much larger data processing audiences. One of the things that I would advise you to be careful is to watch out for less mature components. Both of the systems are having areas that are relatively new, and you need to watch if you are going to use them for production.